Welcome back to the podcast, everyone. Mark here, and Jenny, you know the drill. Today, we're diving headfirst into something that sounds like it's from a sci-fi movie, but is very much real. Probabilistic computing. It's going to really reshape how we think about computers, I think.
I'm so ready for this, Mark. You've been buzzing about p-bits for weeks. From what I've gathered, it's not quite classical, not quite quantum. It's like its own distinct thing, right?
Exactly. It's this third paradigm that just makes so much sense, especially when you consider what current computing, struggles with. Imagine, instead of fighting the inherent noise or randomness in tiny electronic components, you actually use it. You turn a bug into a feature. It's like thermodynamic judo, I call it.
Weaponize noise? Okay, you've got my attention. How does turning something that usually causes errors into a computational asset even work? My brain is already trying to, wrap around that one.
So, classical computers want a perfect zero, or a perfect one, right? Quantum computers deal with probabilities and superposition, but they need extreme cold to function. Probabilistic computers, on the other hand, use what they call p-bits. Instead of being a fixed 0 or 1, a p-bit naturally fluctuates between states, almost like a coin continuously flipping in midair.
Okay, so like a dimmer switch for a light, rather than just on or off? It's constantly moving, not just, settled?
That's a great analogy, Jenny. And because they're constantly fluctuating, they're inherently probabilistic. They naturally model uncertainty, which is fantastic for things like, say, medical diagnostics, weather prediction, or even complex logistics problems where you're dealing with ambiguous inputs. It's like the computer is thinking in shades of gray, not just black and white.
That's fascinating. So if standard binary logic is too rigid for certain real-world problems because the world itself isn't always neat and tidy, these p-bits are a more natural fit. It can already hear our listeners thinking, but how is that more efficient?
Great question. This is where that thermodynamic judo comes in. Instead of expending a ton of energy trying to force bits into stable, deterministic states, probabilistic computers actually times leverage times thermal noise. They're built on materials that naturally fluctuate. This means they don't need all those clock cycles, all those transistors, just to maintain perfect states.
So they're just letting the universe do some of the heavy lifting, essentially? That sounds incredibly energy efficient. And you mentioned it's a bit of a rival to quantum computing too, right? Or, a complementary piece?
Not so much a rival as a complementary approach that fills a very different niche. The biggest win for probabilistic computing over quantum, for now, is simply that it works at room temperature. No need for cryogenic labs, no liquid helium, just your standard operating environment. This instantly makes it far more practical for many applications, and significantly easier to scale.
No cryogenics, that's a huge deal. Quantum computing is certainly impressive, but the infrastructure is, let's just say, a complex fortress. So, if these P-computers can run at room temp, what kind of real-world impact are we talking about here?
Jenny, this is the exciting part. Researchers at UCSB, that's the University of California, Santa Barbara, have already developed prototypes based on spintronic technology, like MRAM. They've shown it can solve complex combinatorial optimization problems, those really tricky puzzles, using incredibly low power. We're talking about a 100-fold reduction in chip area and a 10-fold reduction in energy use compared to classical CMOS for similar tasks. It's quite remarkable.
100 times smaller and 10 times less energy? That's not just an improvement, that's a transformation. So, imagine your phone solving complex routes or medical diagnostics, not just sipping microwatts, but doing it in a fraction of the space.
Exactly. Or hospitals running complex diagnostics without needing massive server farms. This isn't just theoretical. It's lab-tested, physics-backed technology. And because of the material science breakthroughs with things like MRAM, this isn't just some abstract concept. It's moving from the lab to fabrication, lab to fab, as they say in the industry.
And you mentioned something about cloud simulations too. How does that tie in?
Right. So before they even build all the physical chips, researchers are using hybrid cloud simulations, even leveraging services like Amazon Web Services, to test thousands of interconnected p-bit networks. This rapid simulation and testing accelerate the development process, speeding up the adoption curve, and giving them confidence as they move towards building larger, more complex systems.
So it sounds like probabilistic computing isn't here to replace classical computers, or even quantum ones, but to specialize. It's finding its niche in solving problems where uncertainty and probability are key.
You've got it. It's not about beating classical computing. It's about redefining the battlefield. It's ideal for those good enough, faster problems that often bog down traditional systems. We're talking about next-gen AI. Perhaps even building systems that mimic the human brain's incredible efficiency at dealing with fuzzy data. Some experts believe million-PBit chips are quite feasible within the next 5 to 8 years. It's a promising trajectory.
Wow, 1,000,000 qubits. That's certainly something to look forward to. I can already imagine future data centers with classical, quantum, and probabilistic modules all working together. Mark, this was quite stimulating. Thank you for breaking down this complex topic into something so engaging.
My pleasure, Jenny. It's a shift in how we think about harnessing what seems like chaos to power our future. And speaking of chaos, let's consider some potential counterarguments. While P-computing leverages noise as a feature, some critics point out that this reliance on randomness could lead to unpredictability in critical applications, like in medical diagnostics, where absolute certainty might be preferred. Classic deterministic systems provide guaranteed outputs, which are crucial for safety-critical situations, after all. What are your thoughts on that, Jenny?
That's a valid point. If you're talking about, say, a medical device that needs to be precise, you wouldn't want a good enough answer, right? You'd want the definitive 0 or 1. So it seems there's a real need for robust error correction or verification if these p-bits are going to be used in such sensitive areas.
Precisely. And beyond that, there's the challenge of integrating this new paradigm. The software ecosystems for probabilistic computing are still early. Designing algorithms that truly exploit p-bit hardware requires new ways of thinking about programming, which isn't a trivial undertaking. This learning curve could slow down widespread adoption, despite the promising prototypes.
Yeah, that makes sense. It's not just about building the hardware, it's about building the whole toolkit around it, right? And if these prototypes are solving narrow optimization problems really well, will that just scale to, like, general purpose computing? Or will it always be a niche player?
That's the core of the debate, really. Some analysts interpret the efficiency gains, the 100-fold area reduction, the 10-fold energy savings, with a bit more cautions. They suggest these current demonstrations are for specific, narrow combinatorial optimization problems rather than broad, general computation. So while p-bit computers will certainly complement classical and quantum machines, they might not be replacing them for everything.
So it's a specialist, not a generalist, then. That nuance is important, I think, for our listeners to grasp. It's not one solution to rule them all, but another tool in, the ever-expanding computational toolbox.
Exactly. Another tool, a potent one, for specific kinds of problems where probability and uncertainty are inherent. Before we wrap up, I think it's worth engaging our listeners a bit more on this. For example, which emerging computer technology excites them most? Quantum computing, probabilistic computing, or just advancements in classical computing? I'm curious what our audience thinks.
Oh, that's a great poll question. And maybe we can ask them, would you trust a computer making decisions based partly on random fluctuations if it meant faster results? I bet we'd get some interesting answers there. Or, can embracing randomness make our devices smarter, or does it risk losing control? That's a good thought-provoker.
I like those, Jenny. We should definitely put those out there. Maybe we can even ask listeners how they imagine using this tech in their everyday lives if it becomes widespread. If million PBit chips are within reach in the next few years, the possibilities are pretty open. And that's all for this episode. Join us next time for more tech insights.
Until then, stay curious, everyone. Goodbye.